The student in his readings in relativity is likely to encounter two different interpretations of the relativistic momentum. Therefore, it will avoid confusion later to present here an explanation of these different interpretations. This will show that neither treatment is wrong, but that the differences are a matter of taste. The classical momentum has components such as p suffix x is equals to m naught dx dt. If in relativity we wish to continue to regard momentum as a product of a mass and an ordinary velocity, then we must modify the mass and write px is equals to m dx dt, where m, called the relativistic mass, is m0 upon root under 1 minus beta square. This is the view that we presented. However, we can choose to regard the mass of an invariant scalar quantity which gives the inertial property of a body. Then in relativistic expression for momentum, we connect the factor 1 upon root under 1 minus beta square with the ordinary velocity instead of with the mass. That is, we can write px equals to m naught dx d tau, in which dx d tau is the x component of a relativistic velocity. Here, the mass m naught is an invariant, and the proper time interval d tau is also an invariant. Such a formulation is useful because it emphasizes invariant quantities. Furthermore, it is consistent with the basic philosophy of relativity. In this sense, relativity modifies our concepts of time and space so that kinematic quantities such as velocity are expected to change, whereas properties of bodies not directly relevant to time and space, such as charge and mass, should remain unaffected. If, for example, we compare the classical expression for momentum px equals to m naught dx dt with this form of the relativistic expression of momentum px equals to m naught dx d tau, the difference between them is seen to be caused by any difference in the value of the mass, but instead by the difference between proper time d tau and non-proper time dt. Indeed, it should be noted that whether we identify the factor 1 upon root under 1 minus beta square with the mass or with the velocity, the origin of this factor is collision measurements is kinematical. That is, it is caused by the relativity of time measurements. Nevertheless, there are advantages of a pedagogic nature to using the concept of relativistic mass. Both the momentum m times vector u and the total energy mc square as have simple familiar forms in terms of relativistic mass m. We cannot simply replace m naught of every classical formula by m to obtain a correct relativistic formula, as u tending to c, m tending to infinite in the relativistic mass formulation, and this gives a plausible explanation for the limiting speed c that a body can acquire. Its inertia increases with velocity, making it harder to increase the velocity further. Finally, the constancy of the proper mass of a body turns out to be confined to perfectly elastic collisions, a rare situation in practice. Since proper mass can vary, it seems less objectionable than otherwise to speak of a relativistic mass that varies with the speed. We shall continue to use the term rest mass for m0 and the term relativistic mass for m.